Back in 1925, when these two people, Uhlenbeck and Goldsmith, they discovered something really important for physics, and it was the electron spin. And they kind of put this diagram into a paper they published, and I hope at the end of the session you will kind of have a little bit of an understanding of what such a diagram shows. And however, when you go back in history, this picture of the people is actually not representative of who they were at the time where they found out. These were the people that found it out. They were very young when they found it out, so I think all of us have we are a young community, so it's nice that we can also think about cool things. And I want to explain what they actually found out with the spins. They were working on something called the Seemann effect, which means that if you put a particle into a magnetic field and you measure some optical properties of it, there can be a splitting. And they could not explain the splitting beforehand until they discovered the electron spin. And what happens is if you have an electron, it can have two properties, spin up and spin down. And if you align it with the magnetic field, then the one that is spin up does not feel any resistance, so it has lower energy. And the other one that is in the other way flipped, goes against the magnetic field, has a little bit of a higher energy. So it feels different energies, and thereby we get different energy levels and a splitting with this spin property. And between those two energy levels, there's an energy difference. And we can do the following. We take this up and down state, and we label the low energy state 0 and the high energy state 1. And then we have our qubit. And it can be between 0 and 1, and it can not only be 0 or 1. This is what a quantum computer does. So spins will help us to build some quantum hardware. And I will talk about some stuff today that is also regarding other hardware properties. And focusing also on biology, like thinking about how we build computers and what properties we need for that. And it will be split into 3 different sections. So first I will talk about standard hardware that people use to build quantum computers. Then I will pass the question about biological qubits. What material is this biological material? And then I will give you your important question probably. How can you access current qubits? And what code can we write? And I hope I can show some live code if time allows. So first, standard qubit technologies. We're focusing mainly on hardware. This is the Google Sycamore chip. I took a picture of it. And it's kind of this thing that you see in big pictures in a golden chandelier. That's the cryostat. And this sits at the very bottom. And it's made from superconducting circuits. Google and IBM both focus on building such technologies. And this superconducting circuits is like a small electric component circuit that can oscillate at different energy levels, and you can address it with microwaves. So kind of you address and calculate by shooting in microwaves. It's human manufactured, and typically, as I already said, in these golden cryostats. And how it looks inside, schematically, is here you have your almost LC circuit with a specific thing called the digestion junction. And this digestion junction makes this normal electric circuit a kind of quantum circuit. And if you make a microscopy picture of it and look at the IBM chip that has 16 qubits, you see that everywhere where Q is, this capacitor is opened, and at the bottom, at the top and the bottom, you have kind of where you address it from the outside to read things in and out. And then there are also connections between the different qubits, so the different qubits can talk to each other. This is how a quantum chip looks like. So what do you actually need to build quantum hardware? You need something that can be between 2 quantum states, which is your qubit. Then you need the different energy levels, 2 at minimum. And then you need somehow a way to manipulate between those 2. And we normally use light or something that's kind of an electromagnetic wave, and that can flip between those 2 states if you put the right amount in. Yeah, and then you need a way to measure your results, as we saw before, that comes from top or bottom. And as we started with spins, we will continue with spins as well. The superconducting circuits are one of the hardware most prominently used in industry. But then currently, there are also other things coming up. For example, these transistor spin qubits. And this is kind of more transistor-like hardware. It also fits better with our current manufacturing processes. For example, Intel is kind of trying to build bigger systems with this. And here, we don't have this oscillating circuit, but we really have like an electron, a single electron trapped in a potential, and this single electron spin is used to calculate. And you don't address it with microwaves, you address it by shooting in electric pulses. And the other cool thing is that you can have not only transistor spin qubits, but you can have diamond and V centers, which are also spin qubits, but a little bit different. What people do is we take diamond, and then you kind of have to put in some impurities. These are nitrogen impurities often, and then you leave a hole in the diamond. And with this hole, you can do also spin properties that make a qubit that focus on, they have two different energy levels that give you the criteria you need. And in this time, you have to shoot in laser light instead of microwave light. It's human manufactured as well, but it can also be used as a sensor. And the cool thing is that depending on the spin, you shoot in light and you can read out fluorescence. And fluorescence is nothing else, it's light coming out from something after you have shot in light. And this is spin dependent, and that is the important property. So you calculate with the spin, and dependent on the spin, you read out changes. That's why it works. So now the question is, are there some things in biology that also give you these properties, that if you shine light in, some light comes out, and they can have properties depending on the spin of the system. And I will show you a really nice animal. It's a jellyfish. It's called the crystal jellyfish. And what it can do is can actually kind of glow in the dark. If you look at the picture, you see that? It has a green border. And it's extremely beautiful. And this is a protein that the jellyfish makes, and it's a fluorescent protein. And there are different modalities in biology that can make color. Normal absorption, where something goes to another energy level, it comes exactly down. And then fluorescence, what we saw is you get to an energy level, you have some kind of internal other state, and then you only go down. And this other state, this middle state, can often be used to put into a magnetic field and measure specific properties there. And the last thing is chemoluminescence, where not something is coming from the outside and light comes back then, but where a chemical process itself shoots light out, which is quite nice. I think chemoluminescence is probably like the coolest thing, but we will focus on fluorescence. Because these are really two cool people. I got the chance to talk to them, and if somebody has research money left, give it to these two people, please. I think they do amazing, amazing work. They're in Chicago, and they recently thought, like, let's take one of these proteins and just try if we can actually use this state that is kind of the middle state and make a qubit from it. Can we actually measure specific things there, and can we actually, for example, do this in the cell? So instead of the diamond and V centers, they were like, yeah, let's just use this biological thing, because it's made by a cell, it's made inside of a cell, it's not done by humans, and it can be replicated very nicely, and they could show this, and it's a really cool thing. So this is the kind of energy diagram from this fluorescent protein. And the problem is that the decay from T1 down to S0, which gives you the fluorescence, is quite fast. So it can be quite slow and fast. So what they do is actually they kind of shoot it first up to the T2, and then from the T2 they go down. So it's a little bit more complicated, only two states, but you can use a qubit. And the really cool thing is that if you attach to this protein, that biology does all the time, we all make proteins that can be very long. So you can take this kind of spin qubit, the fluorescent, and then you kind of elongate whatever you want to it. It will be close proximity, and depending if there is, for example, a magnetic or electric thing from what you want to measure, this spin qubit can be your readout sensor inside of the cell. So that's pretty cool. So we put kind of quantum computing in cell environments, and it has some also nice properties. And the decay time is, of course, a little bit shorter than if you work at cryo, but I think the future is very nice. That's okay. And the other thing that you can do is, like, this was what I part was of, we put biology into quantum. So we can put quantum into biology, or we can also put biology into quantum. And from measuring, for example, optical properties of such proteins, you can have an optical cavity, and it's kind of two mirrors that have a very, very high reflective rate, so a light bounces off all the time between those two, and it's very, very small, so not much fits in there. But if you put something in there, you can measure it a lot of times, and then because the quantum cavity makes this very nice resonator, something can be detected that is a much better curve than you would get just looking at it once classically. Yeah, but it still leaves a lot of open questions, and I think the most important open questions for you are not what people do in the laboratory, but how you can go to the hardware, and how you can write software, because I can talk code, but I can also write code, a little bit at least. So there are 4 different programming frameworks that are often used for quantum. it's Qiskit, that is closely connected to IBM. There's Cirq, that's closely connected to Google. There's Qwist, which is kind of started independently at Fraunhofer, and Silk, which is kind of closest to C#, and that was developed at ETH. And I will show you now how we can actually look at this hardware with those three, and we will start with Cirq. So if I go here, let's see. Yeah, you see my whole screen. So I just kind of can import this normal. I can import Cirq after I've just installed it. I can also import Cirq Google. Yeah, let's see if this runs. Nice. So what I can do now, if we want to see which quantum computers Google has, we can just write Cirq Google devices. And you remember the thing that I showed you very in the beginning, this blue underground and the chip in front, it was the Sycamore chip. So let's see if we can access Sycamore. Oh, yes. So we see this is the qubits that sit on Sycamore. So it's larger than the image that I showed you from one of the early IBM qubits. And there's also a small sister of it. So this is the Cirq. If you go to Cirq Google, devices, and they go Sycamore 23, you get like another smaller part of the family. So this is the hardware, but we cannot access it, like not everybody can access the Google hardware. But what everybody of you gets is from IBM 10 minutes of free hardware access per month. And I think we can do this together now. So access to IBM's quantum computers in 2025 has gotten more complicated than it was before. So what I learned is that if you don't want people to access something for free, put a lot of barriers in between, and it will get every harder. I will go here back slowly to the slides. So if you want to get your 10 minutes of free quantum time, what you have to do is, this is like an instruction. You go to quantumcloudibm.com. You sign into the cloud platform. You land on the IBM quantum platform. At the bottom, you can see the hardware, which is a good sign if you see this. Then you create a free plan instance. You get 10 minutes. And then, if you have your 10 free minutes, you go back, you create an API key, and then you can use this API key wherever you like. So I can show you now how we do this. OK, so import Qiskit, and we import some other things. And then here's a token. You can use my token for today. After that time, I will delete it. So yeah. And then we access your backends here. And I've run this before, so that I will run it together with you again. And now we see all the backends that we can access for free, so which are free quantum computers. And then the one that's where least people are working currently, I will just use this one. And then if you want to build a quantum circuit, you need to have the qubits, and then you need to apply those gates, like those microwave pulses and everything else. And in your code, you don't have to say, give this a microwave pulse of so and so long. We just define some specific gates. And gates are kind of the languages that quantum programmers work with. And over time, you will get more use what an H gate is, what an X gate is. I don't want to bother you with all the maths at the moment. And what you will get is like a short diagram. And you also have to measure those things so that you actually get a readout from the qubit in the end. And then this is how our quantum circuit looks like. We have a header mode gate, 2 controlled X gates, like the controlled flip gates, and then measurement gates. What we next have to do before we send it to the quantum computer is we have to transpile that, because it needs to fit our backend. So if I kind of draw the compiled quantum circuit, let's see how long it takes. You will see that here, the gates have changed, right? So here we have some kind of gates that were defined, but now they look a little bit different. And this difference comes because the gates that the quantum hardware itself can do with the microwave pulses are a little bit different from the universal gate type that we use when we write more high-level quantum language. And therefore, this is what the actual quantum computer will then run, and it will be equivalent to the one that I have specified. And now what we do is we kind of go and want to use a sampler. We want to get just random, like not random counts, but the counts that come out from our quantum circuit. There's also, if you don't want to sample, you can estimate specific values, like you get an estimation of something instead of sampling just from your qubits. And then I just go to sampler.run. I give it my compiled circuit. I give it how often I want to run this code. And then it runs the job, and it will return the results. And it will take some time. But I hope maybe it compiles, like it runs through while I'm speaking. Yes, it actually did. So we now, in the time while I was speaking, we went to IBM hardware, ran our circuit there, and they came back to us. That's quite nice. So these are our results. They're quite incomprehensible. But if you know how to access and get your counts, you will see that from our bits, we had 3 bits in our circuit. We measured 431 times, all of them in the 1 state, which was the higher energy state. And 512 times we measured in the 0 state, and we did not measure any other combination. So these qubits were kind of entangled, which meant that they kind of knew what each other were doing. And they always wanted to do the same thing. Either they wanted to all be 0, or they all wanted to be 1. And the other thing that happened here was we saw that the quantum computers are not perfect, so we get some noise. And the noise is the thing that is kind of, that should not be here. If you would use a simulator, as I said before, Circ, for example, gives you simulators, you run the same thing, but you get, like, you put your air simulator as backend. So you got this, go through the same thing. And now you see, oh, you only get those 2 perfect, clean things. And then if you run the histogram thing, you will see, okay, you only really have those 2 perfectly entangled states that were running on the simulator. The problem with the simulator is that we can only run about like 30 qubits, on 30 to 40 qubits. After this, we cannot calculate anymore, because every qubit you add, you need double the compute, right? So if you go from 30 to 31, you need to double your compute. If you go from 31 to 32, you need to double your compute. And the last thing I want to show you is like how simulators, however, can run still, like small problems. And this is the nice language CRISP. And I will show you how to run the Shor's algorithm with it for a small number. What Shor's algorithm is doing, it takes a number that is it's multiplied from between 2 factors. And if you don't know, for example, what the factors of the number are, Shor's algorithm helps you to find out what those 2 parts are. And this is the algorithm that kind of does not help RSA, because RSA is relying on this problem being hard, and the quantum computer makes it more easy. And we want to factor the number 15, so n is equals 15, and there's like a little bit of small code. So we kind of get our quantum register here, and then a little bit of code to run it. We also do quantum Fourier transformation to later get it back. And it will now start running, and it's on this device locally, so it's like very low, but we simulate 18 qubits. 18 qubits run fine, we get some results. And then we do classical post-processing once, and see if this was kind of a neat shot. It was. And now we should get, which factors does 15 have? Who can give me the 2 factors of 15? Yes. OK, let's see if it did that. Yes, first factor is 5, and the other factor is 3. So we all ran Shor's algorithm on a simulator. So we can also run it on a normal hardware. But it was not so much code, was it? I think this is quite OK. Yeah. So going back, and I hope this was crisp. Many cool things, I think, will come out from having programming languages that are more high level. And the Shor's algorithm, the first time it was run, which kind of brings our talk right back to where we started, was on this molecule. And it was run on not electron spins, but nuclear spins. And when you read this paper, this paper is like just a few days older than me. And it's quite nice. They said, OK, they factored number 15 in the laboratory using this molecule, because at that time we did not really know how to build quantum computers, but we could use molecules to calculate quantum stuff. And they used these 7 spins here, and these are the 7 spins. And that's it. So I think the thing that I want to leave with is let that be fluorescent light, and let there be some good code. Yeah. Thank you.